third session of the Industrial and Fine Chemicals. I'm Randy Yates from Shell, and my co-chair is Damien Gironnet from the University of Illinois. It's a pleasure to have a keynote speaker today, Professor Bert Chandler. Professor Chandler received his PhD from the University of Minnesota, working with Professor Pinelay. He then did a postdoc in the CME department at the University of South Carolina and joined the faculty at Trinity University in 2001. Trinity is a small private university in San Antonio, in the great state of Texas. And Professor Chandler has the opportunity of working primarily with undergraduates. So it's an interesting program. But he will be talking about improving the selective oxidation of carbon monoxide present in gaseous streams using supported gold catalysts.
Thanks very much, Randy. Can everyone hear me okay? So, yes, I'm from Trinity University, and as we like to say, it's a place where we're unencumbered by graduate students. So I do want to thank the people that did most of this work, especially Johnny Savier, who was a postdoc with me for a couple of years. It really is a fantastic colleague and friend. Todd Whitaker is still around doing some procs. And then especially our collaborators, mostly these are computation people, Hugh Donovan, our grab out of Houston, and Gaurav Kumar and Mike Janik at Penn State, and Rob Rube has done a lot of characterization work for us and also been really helpful talking today. So I modified the title a little bit to more accurately represent what we talked about. Basically, we talk about how we can change the activity of gold sites and monitor some activity. Right? So, as I'm sure you know, we use a lot of hydrogen here, and in this audience, more you guys know more about this than I do. But basically, hydrogen production is going to need to increase just for food. You can expect we need roughly the equivalent of 3 new hydrogen plants per year, probably for the next 20 or 30 years. Right? And as I'm sure you guys all know, hydrogen is produced from steam reforming, water gas shift reaction, and what comes out of the shift reactor is a feed that has nominally 1% CO in hydrogen. And that CO has to be removed before you can do anything else with the hydrogen. So the typical hydrogen purification methods are methylation and pressure swing absorption, and we're not going into too much detail on those. They have their pluses and minuses that are used in different areas. One interesting method could be the preferential oxidation of CO. For methylation especially, you have some energy losses due to the loss of hydrogen that's used to make the methane. Preferential oxidation, what you'd like to do is instead of convert the CO to methane, add a little O2, selectively burn the CO and not touch the hydrogen. And this has been limited by the catalyst activity and selectivity. Right. So why hasn't this worked? And that might be a little too loud. Why hasn't this worked? And the simple reason is that prox is tough to do. And it's really tough to do. So if you just think about it, at the top of the reactor, you have maybe a 100 to 1 hydrogen to CO ratio. At the bottom of the reactor, you need to be able to get to where you can react about 10 to the 6th CO, hydrogen to CO ratio. You got to pull out that 1 in a million spot. So nominally, your CO oxidation rate needs to be about 1 million times faster than H2 oxidation. Let's just sort of back of the envelope just to give us some perspective. If you think about it, gold ought to work for this. We've known for a long time that gold is a wretchedly bad hydrogenation catalyst. It has a good selectivity for things, but it's really just not, it's not good at all compared to platinum, palladium, and nickel. We also know, we've known for 30 years, actually this year is the 30th anniversary of the release of Professor Haruta's paper that showed gold has excellent CO oxidation activity. So that makes this a fundamentally interesting problem, which is where we've come into it and tried to approach it. We try to understand what makes CO oxidation so fast, and then how do you control these competing oxidation reactions? They must be pretty similar, they're both using O2. And then do these reactions occur at the same active site? So this is our overview, and we are certainly not the only people that have worked in this. I've listed a few papers over here. Javier Guzman's published some important work on this. Other important factors that people agree on are that oxygen absorption is extremely weak on gold. I don't think anyone has ever observed O2 directly bound to gold. It's certainly not the surface science system. The metal support interface seems to be critical and important for these reactions. The support, there's a lot of lore about the importance of support effects for gold catalysis, and it clearly is important. There are differences from one support to the next. Surface hydroxyl groups appear to be important for if you have a catalyst with no hydroxyl groups, you see essentially no reactivity at all for CO oxidation. And water's been known to be important for about a decade or so. There's also a lingering debate about oxygen vacancies and their potential role in CO oxidation. These are some of the things that are generally agreed on and we'd like to discuss a little bit. Our interest has been specifically, and at least what we'll talk about today, is the role of water and hydroxyl groups and potential oxygen vacancies. And then we're interested in developing kinetic tools to better understand some of these so that we can improve procs and understand some of these support effects. All right, so I'm going to start by talking a little bit about water versus hydroxide. Most of this is on, most of the data I'm showing you is on titanium. We also have good data on lithium as well. So basically, if you start with a catalyst, and Johnny did these experiments about 3 years ago, I guess. If you start with a catalyst and just slowly remove the water, so it's really gently pre-treated at 20 or 70 degrees, so at a place where you're really not going to dehydroxylate at all. You can see the hydrogen-bound OH stretching frequencies go away. The dangling OH associated with hydroxyl groups sticks around. And when you do this, we see there's no change in the OH area, and the turnover frequency drops by an order of magnitude. So this indicates that these hydrogen bonding groups are kind of the key species for this. We also compare this to the plot of activity versus water pressure. This is now starting from no water and adding water to the feed. You see that the activity is much more dependent on water. So this suggests that the hydroxyl group is really not directly involved in the oxidation reactions. And probably their primary role is to provide water binding sites. So we believe, based on these, that water is the key catalytic species for this reaction. To help confirm this, we've done some kinetic isotope effect experiments. We aren't the only people that have done these. We just did them a little bit differently. Essentially, if we just exchange the protons for deuterons, so exchange D2O for H2O on the surface, we can remove all the H2O, and we get a kinetic isotope effect of about 2. So this really implicates OH bond breaking is involved in the rate determining step. Now, if we then add water and do to the reaction, we see that the rates come up, as I just showed you, but the equilibrium, or the isotope effect starts to go away. And then if we take the water away, the rates come back down, and the isotope effect comes back. So this actually indicates that there's some saturation kinetics with water in the reaction. And our values with high water are actually pretty consistent with those measured by Harold Kong's group and the Gaseous group a few years ago, that show really much smaller kinetic isotope values that are then consistent with this equilibrium isotope effect. So I think that our data is actually pretty consistent with these other reports of literature. Okay, so one of the things that we've tried to do in terms of these reactions is try to think about them a little differently. And one of the things that's been really useful for us has been Michaelis-Menten analysis, or thinking about things in the Michaelis-Menten tool. And a lot of this is really about language and guiding our thinking more than advanced kinetics. And what I would like you to think about, or at least how I want you to think about it, is that if you think about a catalyst, well, it's a surface, and it has some active site, or some series of active sites that form a reaction. Organic chemists and biochemists really think of proteins in much the same way. That the protein is a surface, and there's an active site where the reaction occurs. So the incoming molecule has to find that active site, just like the incoming molecules have to diffuse to an active site on a heterogeneous catalyst. So the Michaelis-Menten language provides sort of a catalyst-centric language to help us describe and think about the catalyst. And in a sense, kinetics is an in-situ characterization tool. So this was our Michaelis-Menten treatment that we developed about a decade ago. And we started with the simple assumption that CO binding is strong and CO is readily available. O2 activation is then the key step. And you can then derive sort of a simple characterization mechanism. This is not intended to be a full mechanism showing all the detail. And in fact, this mechanism isn't quite right. But it's still useful, which is actually one of the things that makes this interesting to us. Right? We can define an active site. Again, we don't have to just describe the active site. We have to say there is an active site, and the only structural requirement that we had at this point was that it binds O2 somewhere near gold CO. So it could be on the support if it's a surface oxide or an oxygen defect site. It could be on the gold. We don't have to actually make that call at this point. Right? So you can use a steady state approximation, derive a rate law, and the key things that you pull out of this are that there's a term for Vmax, which is related to the intrinsic activity, or at least the rate determining step of this simple mechanism, and then the total number of active sites. And then we also get a Kr value out, which can be interpreted a couple of different ways. One way is interpreted as an assembly equilibrium, so a net equilibrium constant for, in this case, O2 binding. The other way to think about it is a measure of the reactivity of the O2, the gold O2 complex or enzyme substrate complex, if you want to revert to the Michaelis-Menten terminology. All right, so this is some oxygen. This is basically the same oxygen reaction order data. It's just plotted as a double inverse plot, and you see that the data is described pretty well. And when we pull out the Kr and Vmax, now what we're doing is pulling out the extracted terms from this as a function of the water pressure or the water coverage. We see a couple of things. First of all, that water doesn't have much of an effect on the Kr value. But it's the same no matter how much water is around. And the other thing we see is that the difference between gold aluminum and gold titanium is actually pretty small, even though there's a lot of information in the literature that suggests these catalysts have quite different activities. At least in terms of this initial step, they look to be pretty similar. What we do see, though, is that water really changes the Vmax value. And it's actually pretty substantial on alumina. The slopes a little gentler on titanium. But there's a very clear trend with changing activity as a function of the water, the amount of water. And we believe this is due to changing the number of active sites, so the number of reactive centers that are available at a given time. So if I go through and compare all of the catalysts, I don't want to go through too much of the details of all these measurements, but we have made kinetic measurements and thermodynamic measurements on gold, on aluminum, and titanium. If we look at the water binding constants, this is water binding, this is the surface of the catalyst, that's the same. CO, O2, water reaction orders are all essentially the same. Kinetic isotope effects are the same, both under wet and dry conditions. The Kr values are pretty close, and for equilibrium constants, it's not a very big difference. If you extract out an O2 binding constant, you get a number that's a little bit larger than 1, which is a little surprising. And Harold Kung asked me about this like 8 years ago at this meeting. I didn't have a good answer for him then, but now I can explain why this is. And so again, this is a little bit surprising, but we can explain. So the key thing from this is that if the reaction kinetics are the same on both these catalysts, they really need to go by the same mechanism. It's really hard to implicate different mechanisms. The other thing that's not shown here that's important is that the maximum activity for these catalysts always occurs somewhere around 1 monolayer of water on the support. We do know that carbonates are important for this reaction. Lots of other people have seen this too. I'm not going to have the time to talk about that in any detail. We think the primary difference in reactivity between these two catalysts is in surface carbonates. All right, so this gives us some insight into potential roles of water, OH, and oxygen vacancies. Again, the hydroxyl groups primarily, we think their primary function is to anchor water close to the gold. We don't think oxygen vacancies are important in this because the maximum activity occurs in 1 milliliter or 1 monolayer of water. If it's at 1 monolayer of water, any of those oxygen vacancies are going to be covered. Additionally, we have the same mechanism on these two catalysts. And if you want to invoke the same, if they have the same mechanism, there's really no opportunity for oxygen vacancies on gold on alumina. That means they're probably not important for gold on titanium, at least when water's around. So I should have that as a caveat. There's certainly a lot of evidence, especially from Bain's group, that oxygen vacancies are important under other conditions, especially a little bit higher temperature. Right. So again, water is the key catalytic species. It affects the number of active sites, and we've seen that OH bond breaking is key. So we think about this water more as a co-catalyst. Is very similar to the conclusions that the Gaseous group made several years ago. So we turn to our friends at the University of Houston, and I'm going to do a huge disservice to them in terms of only talking about all the work they've done in a couple of slides. And really it took them about a year to generate the DFT model that we used to get this data. The key things that they did were to generate a DFT model that had a fully hydroxylated titanium surface and then add 1 or 2 water molecules. And when we do that, we see a couple of interesting things. The first is that O2 is bound in a barrierless, via proton transfer from water in a barrierless reaction to generate gold OOH, or some probably gold peroxide species. This reacts then very quickly with CO to form another downhill reaction to form gold carboxylate, and then the decomposition of this gold carboxylate looks to be the rate determination step. This involves a proton transfer back to water or toward the support, and that kinetic isotope effect value that they calculated is about 2.5. Ours was about 2, to remind you. So I think we're in pretty good agreement between those two steps. Right, so this is that mechanism just shown in a little more cartoon form. So we've got O2 comes in, binds, it pulls a proton off of water as it binds, then it reacts quickly with CO to form the gold carboxylate, and then the decomposition of that gold carboxylate with the proton transfer back to the water is the slow step. And then the reaction is finished up with CO and oxygen atoms reacting. So you can draw now a much better stepwise mechanism for this. You can derive Langer-Hinshelwood type rate law for it. You can then do a double inverse plot, and you actually end up with the same value, that this 1 over, that the Kr value ends up being 1 over K3, which is the oxygen binding constant. And if you're an inorganic chemist, you can draw a 2 electron pushing mechanism and follow all the electrons and all the oxidation changes all the way through. So we feel pretty comfortable with this, at least it's consistent with all of the data that we have. All right. So that's sort of our story for understanding CO oxidation. And the question is, can you use this to improve PROX? So again, just to remind you that PROX is tough. We need to get the reaction rate for CO to be about 1 million times faster than H2. And the target that's in the literature is not only 50% selectivity with less than 50% or 50 ppm CO in the feed. Right? So there's a lot of people who worked on this, and there's lots of different data. People have used different gold catalysts, different reaction temperatures, different space velocities. So we decided to compare all this with a simple figure of merit. So all we're going to do is define the O2 selectivity divided by the CO slip to describe performance. And to hit this goal, we need to get a value of 1. So this is the data that we've been able to find in the literature. There's a myriad of different supports. There are a couple of examples. These are all from Hutchings group that have beat this goal, but they're at pretty low activities. Now, if we control the water and space velocity, we can essentially beat this 50-50 goal and beat the previous literature by about 1 orders of magnitude in overall performance, at least defined by this figure of merit. And then we can operate at roughly an order of magnitude faster, space velocity or faster nominal activity. And I'll show you all the details for that in just a second. And I also want to add that this is data with an unoptimized oil root cast. This is off the shelf from Stroud. We haven't done anything fancy at all other than trying to understand the kinetics and the reaction mechanism. We have similar data for gold on titania. It's a little more active and a little less selective than gold on titania. Right, so if you control the water pressure carefully, you can drive the CO slips down to just a few parts per million. And this is down really architecture limit. It's probably 2 or 3 parts per million. And really this acts like essentially, and then we're like a nearly sequential reaction. So if you're at a low space velocity, you get very low CO slips, makes it react all the CO out, start flowing a little bit too fast, then you're flowing a little too fast for the catalyst. And similar with O2 selectivity, if you're flowing fast, you're really only reacting the CO. If you start flowing too slow, you start burning a little hydrogen at the bottom. So this makes sense with a very consistent, almost stepwise mechanism for the two. Water helps in other ways as well. In terms of selectivity, with water we stay up about 75–80% selectivity. This is at 60 degrees, I think. If as soon as you take water out, your selectivity drops to around 60%. It also helps with longevity. If we run with water, at least over the time frame of this experiment, which is about 10 or 12 hours, we don't see any deactivation whatsoever. This line actually has a slight positive slope. Without water, you lose activity right away. All right, so why does water improve PROX so dramatically? Well, it turns out that for all the reactions that we run, we've done this at several different temperatures, we always see a maximum activity in this window that corresponds to about 1 or 2 layers of monolayers of water on the support. And we think that's basically just making sure that there's plenty of water available to do the O2 activation step for CO oxidation. We know that in doing this, water actually physically blocks about half the gold site. So this is a plot of a CO absorption isotherm we measured in the IR as a function of water pressure. So what we see is if we add water, and this is at room temperature where 2.5 torr is about the maximum activity for the reaction, we've actually blocked about half of our CO oxidation sites. And we don't think water is absorbing on gold. There's really no precedent for that in the literature. We think it's just physically blocking the sites that are at the metal support interface. So we've more recently done some H2 activation studies and looked at the kinetics and the kinetics of both H2 oxidation and CO oxidation. First thing I want to point out is that the O2 activation kinetics or reaction orders are essentially the same for both. This indicates they're probably going through the same intermediate, and they have observed some similar things as well in their systems. The second thing is that we see that water actually inhibits H2 oxidation. So what we think is happening is that water is actually sitting at the metal support interface, and that those sites are the key sites for H2 oxidation. Others have reached that conclusion. as well. So as a cartoon to show this, again, if you have a little bit of water around, the catalyst is damp, you need that water to generate protons for O2 activation. But if you have open sites that are available at the metal support interface, you can do the H2 activation as well. When the catalyst is wet and you have 1 or 2 monolayers of water on support, you now block those H2 absorption sites. But still, there's enough water around to access for O2 oxidation, O2 activation to CO oxidation. So if you think about it, this is a little problematic. In some ways, the catalyst is too good because now if you get rid of all the CO and you work with 1% O2, then you still have 0.5% of O2 in the feed you got to get rid of. So we looked at trying to monitor the metrics or measure the metrics a little bit differently and see if we could get a better way to get performance. So this is looking at the CO slip as a function of space velocity at several different O2 pressures. The first thing you see is that you really need to get about 1% O2 to drive this reaction, the CO oxidation reaction to completion. The O2 slip, though, if you use 1% O2, well, then you have a little O2 left in the reactor. You can get rid of all of the O2, but then you've got some CO left. So this is a little bit of a pain to think about. And then we realized, we sort of scratched our head and said, it's really not that hard to burn hydrogen and get rid of O2 when you have hydrogen around. So what we did is we just threw in just a cheap nickel catalyst at the bottom, and we said, and did the same reaction. Basically, the idea is to use the little bit of hydrogen to hydrogenate off the rest of the O2. And so what we see is that if we use higher O2 pressures, we can drive the CO slip down to essentially our detection limits. And then if with the other catalyst at the bottom, we can get rid of all the O2, you may have to optimize it a little bit to get rid of O2. More O2 depending on your conditions. But essentially, you can choose the purity of hydrogen based on how much, choose the purity based on how much hydrogen you're willing to sacrifice. So if you want to get down to a few ppm O2 and a few ppm CO, you can do that. You just have to sacrifice a little H2. So kind of moving on, we want to try to understand a little more why are these catalysts different and why are there support effects in gold, especially in gold catalysis. And this really gets down to what we really want to be able to do is develop kinetic tools to help understand differences in active sites and really look for more fundamental questions than anything else. So to do this, we've been working with benzyl alcohol oxidation and looking specifically at substituent effects on benzyl alcohol oxidation. Now this is a simpler reaction in some ways in that the mechanism is pretty well understood, or at least well agreed upon, and it's pretty clear that the rate limiting step is a hydride transfer to gold. To gold catalyst. And this is based on Hammett studies, which show a resonance stabilized positive charge in the transition state. I'll talk about these in just a minute. And also some spin trapping studies that show gold hydride forms during the oxidation reaction. What's interesting about this is that even though these are both reactions, we see the complete opposite support effects for gold on aluminum versus gold on titanium. So for CO oxidation, gold on titanium is faster. For benzyl alcohol oxidation, gold on aluminum is actually quite a bit faster than gold on titanium. Right, so we went back to our double reciprocal plots to look at this data, and we see a similar trend in that the Kr values are pretty similar, suggesting that the assembly equilibrium is pretty similar for both of these reactions. But now we see a pretty large difference, a factor of 20 in the Vmax values. So the Vmax value, there's two limiting factors, the way to think about this. The first is that there's a 20-fold increase in the number of active sites on gold on alumina. Those particles are a little bit smaller, so that there probably are, we know there are a few more active sites there. But the other possibility is that the intrinsic rate constant is quite a bit larger. And we think this is more likely. We don't think there's 20 times more active sites, 20 times greater number of active sites than gold on aluminum. We've measured that. Right, so we can go through and also make sure that water is not a huge factor. We see about a factor of 2 difference in the Vmax when we dry the catalyst. The Kr values are also very similar, indicating that we're not fundamentally changing the reactivity. Here we're just changing the number of active sites, but we still are left with this total number of active, or the large changes in Vmax based on these 2 catalysts. All right, so the key difference, this appears to be a difference in the rate constant, or they're driven mostly by the rate constant. We've converted these to TOFs, and the story is still essentially the same. But we wanted to at least think about this in terms of the mechanism. So what we think is happening is that we have benzyl alcohol absorbing on the support. You can see this by lots of other methods. And then there's some level of proton shuttling or proton transfer involved to basically get an alkoxide at the gold active site. Both the DFT studies that Mike and Gaurav have done have shown that we really need to have an alkoxide here, at least some way to help stabilize the hydride transfer, which is the rate determining step. So essentially we have the assembly equilibrium of getting the alkoxide near the gold nanoparticle, and then the hydride transfer as the rate determining step. Okay, so Hammett studies have been important, and what we've been trying to do is use Hammett studies to help understand what some of the differences between these catalysts. So I'm going to have to walk you through this because I realize some of you may not have had a physical organic chemistry class in the last couple of years. So what Hammett studies do is they're linear free energy relationships, and they allow us to correlate thermodynamic and kinetic properties. So the Hammett study is based on the relative acidities of benzoic acid. So if you have an electron donating group, you make benzoic acid less acidic. If you like to have an electron withdrawing group, you make it more acidic. We can define this term sigma, which is essentially an experimental measure of the electron donating and withdrawing ability of a substituent. So when you plot the log of a rate versus sigma, you're essentially doing a log-log plot to look at how electron donating and withdrawing affects the transition state. So what we have here is a Hammett plot for gold on alumina. So you have an electron donating group, methoxy, they help activate the reaction or make the reaction go a little bit faster. Electron withdrawing groups like CF3 make the reaction slower. And this correlation suggests that this is involved in this particular correlation, the negative slope suggests that there's a positive charge buildup because the donating group can help stabilize the positive charge, and the withdrawing group destabilizes it. And this has been used this type of study has been used for 60 years or so in organic chemistry to help understand active sites. So there's a lot of chemistry to support this idea. And Corman initially did these studies to help identify the hydride transfer as a rate determining step in CO oxidation. Okay, so our rationale for thinking about this is that, well, rho is a measure of charge buildup on the benzoic carbon, and that's well established by lots and lots of chemistry. But if you think about it, that carbon is transferring that hydride to the gold, into the metal. So therefore, this should be at least partially compensated by some negative charge buildup on the catalyst, and therefore rho should depend both on the reaction and what's happening with the substituent and the catalyst. So we think then that we should be able to, or our idea was that we should be able to use Hammett studies to probe the active site electronics. And sort of the unique thing about this is it only probes the active site. It's not a global measure of electronics. It only probes the active site because we're using the catalysis as the probe itself. Right? So when we go through and do these experiments, now these are 4 different catalysts, and we see there's a pretty large change in this rho value from almost 0.9 to about 0.36. This is much larger than we expected. We thought we were just doing control experiments and this would all work out the same. But it turns out the support tunes the gold to a much larger degree than we initially thought it might. So basically the way to interpret this is that the changes in rho suggest that the hydride transfer to gold on zinc oxide is in a sense harder to do than the hydride transfer to gold on alumina. And that suggests that what we're doing is we're making, with different supports, we're making the gold either a little bit more electron rich or a little bit electron poor. And I should say this is the gold at the active site, which may be a subset, is almost certainly a subset of those all sites. Okay. So and actually, Bruce was talking about this earlier this morning. This is essentially the same idea as the support acting as a ligand, and acting as a ligand to gold. And one of I think the unique thing about Hammett studies is they really provide a potential very sensitive tool to probe that active site. I should also say that the rho value correlates very well with the benzyl alkyl oxidation turnover frequency. Now we've correlated everything for particle sizes effects based on thiol poisoning studies. Right? So what are the origins of this support effect? We really like to understand. So we can go through and try and correlate these rho values with lots of things. There's no correlation whatsoever with particle size. These particle sizes are all pretty similar to begin with. There's no correlation with support with basicity. That's one thing we kind of worried might be an issue, but there's no correlation here at all. There is some sort of qualitative things that looks like in XPS and the band gap that suggests that this is a function of electron donating ability of the support. We wanted to try and nail that down in a little more quantitative or semi-quantitative way. So again, we turned to our friends with DFT skills, and this was Mike, Janet's group in New York, Mara. They've done a lot of work on this, and we'll talk about a little bit how they've helped us understand some of what's going on. So what we did is we tried to model just the rate determining step for this reaction. So we're not trying to do the whole experiment. And essentially, the first thing that we found is that you really have to have a base there to do this reaction. That you need to have some form of alkoxide or an ability to get rid of this proton in order for this reaction to go. Right? So we modeled the gold as just a simple 35 atom cluster, and we modeled this basicity with just a simple gap. Right? And again, the focus here is just to look at how the hydride transfer changes as we change the catalyst. Right? So focusing on this step, we found that the activation barrier is a function, or is linearly scaled with the reaction energy, which makes life easier for the DFT people. And then we can go through and calculate essentially all the transition states or delta E's for the reaction, and get sort of qualitative DFT rho values. And these DFT rho values show that as you go to a more electron-rich cluster, so you just put a negative charge on this cluster, if you go to an electron-rich cluster, you get a fairly flat rho value or a small rho value. If you go to an electron-poor cluster, you get a larger rho value. So it's entirely consistent with what we see experimentally. And these values too, this -2 may seem like a large charge on a cluster, but if you average that out over 35 atom cluster, you're looking at about 0.05 charge per atom. So I think this is actually a pretty reasonable approximation for what might be going on the surface of the support. Right? So they did a number of transition state calculations. This shows you the transition state for the reaction, and it does move a little bit based on charge. So I'm showing you both for 3 different substituents, and then the CH bond distance, which is just an average this CH bond distance in the transition state. So for negatively charged clusters, you see it's a very late transition state. The CH bond is essentially broken in the transition state, no matter what the substituent is on the benzyl alcohol. For a positively charged cluster, it's a very early transition state, so you just have to begin breaking the CH bond, and then the hydride moves onto the gold. So essentially, the negative charge on the cluster, in a sense, has a repulsive force on the hydride transfer step, which makes sense. So therefore, making electron poor should increase the reaction rates for this reaction, which agrees with our studies. So where does this come from? The last thing that we did was try and correlate some of the experimental DFT or experimental rho values with the work function, which is how we sort of thought the easiest way to evaluate or quantitate the electron donating ability and support. We tried to make some measurements for these. Rob tried to help us out with some of these measurements, but they're difficult to make on the actual catalyst, so we reverted to DFT. We see that there's a pretty reasonable correlation between the experimental rho value and the DFT work function. Again, kind of indicating the support is acting as a ligand to help tune the active sites. These values are a little bit, there's a lot of variance here. The y-axis here, the y bar shows the experimental error and the rho value measurements, and the x bar here is really showing the range of values that are available for the different supports. We had to try several different structures of the support to get to this. Okay, with that, I'm going to finish with that and kind of remind us of where we've been. So look at the roles of water and OH and potential oxide vacancies, at least under these conditions. We think we can improve prox pretty dramatically. I think we think we understand the chemistry pretty well and have converted this essentially to an engineering problem now, which happy to let the engineers work with. We really like this idea of developing kinetic tools to think about and explore active sites. We think there's a lot of room to start measuring some differences and understanding differences between catalysts here. And that electron donation can play an important role with these catalysts and can at least account for some of the. We're going to finish with that. Origins of support effects. And finally, I want to thank the people that did the work. Dr. Johnny Saavedra, who is now at PNNL, really was an outstanding postdoc and did a tremendous amount of work in about 2.5 years, which included moving our lab into a new building. Todd Whitaker is continuing the proc studies now. So he's a student just graduated from my group and is just stick around for a year to play and do research. And then my colleague Chris Mazzell, he works with me very closely on a lot of this. Does alcohol oxidation. Luke Tibbetts did all the Hammett study work, and we have some other students that are continuing some of these things. And then I really want to thank my colleagues for all of their conversations and help with DFT. Mike Janik's group and Rob Rue at Penn State, and then Lars Grabo's group at University of Houston. And I'd like to thank you and thank you, the organizers, again, for giving me the opportunity to tell you about what we've been doing. Thank you very much.